In this last section of chapter 11, we're going to be talking about arc length. And the idea behind that is simply computing distance between 2 points. If we have our regular coordinate system and I just pick 2 points on it, let's say this one and this one, if you give me coordinates for them, I can compute the distance between the 2 points directly, right? So the shortest distance between the 2 points is a line. So in order for me to compute the distance, all I need to do is know the coordinates. So let's say x1, y1, and x2, y2. And then the distance, if you guys remember the distance formula, or you can think of distance as being computed in terms of Pythagoras theorem, right? So in order for me to compute the hypotenuse here, this guy, it's the square root of the squares of the two sides. And the squares of the two sides, of course, are the differences in the y-coordinates between the 2 points and the differences in the x-coordinates between the 2 points. So the distance formula altogether gives me square root of x2 minus x1 squared plus y2 minus y1 squared, where again x2 minus x1 is actually this portion, and y2 minus y1 is actually this portion. Now, for non-straight lines, so for example, if we have a piece of parabola and I would like to calculate the distance along it from this point to this one, it's no longer a straight line, but we apply a very similar idea to calculate non-straight line segments. Okay, so if I would like to compute the distance between, let's say, this point and this point, it is, of course, a curved length here, but what we can think about is splitting it up into small pieces, small enough where every piece in between is essentially a little straight line. Okay, so let's have a sort of zoomed in version of this idea. So let's say here's my curve. I'm going to pick 2 points on it, this one and this one. And if I zoom in far enough, these 2 points will be connected by a straight line. I'm specifically drawing it so that it's not straight to illustrate it, but we're going to think about a limiting procedure where they are actually straight. So then what I would like to compute is this distance. And once again, I'm going to think about that in terms of my vertical displacement and horizontal displacement. Why do they look so weird? Let me just redraw that. Whoops. So this is going to be in terms of vertical and horizontal. Okay, now because I'm going to be splitting them into tiny little pieces, this is what we call dy, the change in y, and this is what we call dx. Now, because again, like this is not the full distance, but rather a little piece, I'm going to be calling it dl, the change in length. So simply from this picture, I have that dl is calculated the exact same way that the distance was here, but now on dx and dy. So it's going to be dx squared, the change in x squared, plus dy squared. Now, really, it's just me rewriting this exact same expression, but in new notation. This is the change in x, and this is the change in y. But what I can do here now is to think in terms of simplifying this a little bit further by factoring out dx from under the square root. So what I'm going to have is, if I take out dx squared, I'm going to have 1 plus, I factor out dx squared, so I'm going to get dy over dx all squared. And then I take out dx squared from under the square root, which leaves me with dx outside of it. The good thing about this, of course, is that we recognize this expression as the derivative of the function, dy by dx. Now, adding up these small segments, so let me just write this up, adding up small, straight, again, they're going to be straight in the limit, segments, we get that the arc length is what we call it. Let me just for now call it length of the curve is. So what I have here is, again, I'm going to be adding up over all of these. Adding up is equivalent to computing the integral. So what I'm going to have is the integral between the 2 points that I'm computing the distance of 1 plus, and then I'm just reading off directly from this. This is what's going to go inside my integral. So 1 plus this expression, which is just the derivative squared dx. Let's now see how this formula works in practice. So once again, let me just rewrite the formula here. So it's between A and B, the 2 points you're computing the distance in between, 1 plus the derivative of my function squared dx. Okay, so for the first example here, I would like to find the length of a line with slope 2 from 1 to 5. Just a quick sketch here. Okay, so I am interested in the length of a line with slope 2. Notice I don't actually know its intercept, so the line itself can lie in many different places, but I'm interested in the length between 1 and 5 of a line of slope 2. So let's say my line goes through the origin. Here it is, slope 2. I'm just sketching, right? So I'm not being too concerned about my scale on the y-axis. So I would like to know the length of it between here and here. Now this example, this is just a line, so I can actually compute it using the regular distance formula, except for, again, I don't actually know what the exact line is. The line of slope 2 can be this one, or it can be this one, or in fact any line that is parallel to this will be a line of slope 2. And notice that in fact the distance between 1 and 5 will be the same on all of them. Okay, so now but I would like to practice using this formula, so let's try that. Okay, so what I have, of course, is now going to have to be an integral between the 2 points where I'm interested in. Notice that the integral is in terms of x, so my limits of integration are also going to be in terms of x. So it's going to be the integral from 1 to 5. And then I'm just reading this off here, right? So it has to be square root of 1 plus my function's derivative squared. My function here is the line. I now have to, so this is my function. I'm not actually given it explicitly. I'm just told it's a line of slope 2. So if it's a line of slope 2, then what is the derivative? The line is always of the form mx plus b. So the derivative of it is its slope. And here I am told that the slope is going to be 2. So the derivative of this line is a constant 2. Now notice that I always have to square the derivative as per the formula. And then I have my dx. Okay, here I can actually calculate this out. So this is going to be integral from 1 to 5 of root 5 dx. So it's root 5x, where x goes from 1 to 5. And if we plug it in, we're going to get 4 root 5. Okay, so the length of an arc you can always compute, and it should always be a number. Let's take a look at the next integral, at the next example where we are given the function explicitly. Again, let's just sketch it so we see what's going on. Okay, so I'm going to have y equals x cubed. And I am interested in the length of the curve that happens between x equals 0, so over here, and x equals 1. So let's say somewhere over here. Right, so I'm interested in this length. It is clearly not straight, so I can't apply my regular distance formula, which means that I will have to calculate it in terms of this integral. Okay, so my function is y equals x cubed. Notice that in the formula I need the derivative. So I'm going to take a derivative here. It's 3x squared. And that's what I plug it into my integral. So my integral, again, being in terms of dx, I have to take the x bounds as the limits of integration. So from 0 to 1, square root of 1 plus my derivative, which is 3x squared, squared, dx. Okay, simplifying this a little bit, I'm going to get 1 plus, if I square everything, I'm going to get 9x to the 4th dx. And if we were to proceed with actually solving this integral, notice that there's nothing else I can do to simplify it, so I have to look at this structure as a whole. It's a square root, 1 plus, and maybe it's actually easier to look at it here. It's 1 plus something squared. There's nothing else outside of this integral, which suggests that I'm going to have to use trigonometric substitution. Okay, so trig substitution. And I'm not actually going to proceed with this. For the majority of the section, I'm actually interested in setting up these integrals rather than really evaluating them. In fact, evaluating them will almost always involve some kind of trigonometric substitution or a heavy integration technique, because by definition you have a square root of some more or less complicated expression, right? So just like with the volumes of revolution, we will focus on setting these integrals up and not worry so much about being able to evaluate them. For an interesting application of arc length, we're going to consider teeth growth in alligators. So for example, for humans, that has been well studied. Humans mostly get their front teeth first and then acquire back teeth as they grow. Alligators, however, acquire teeth in an interesting pattern because nature had to take care of the fact that alligators have to be able to consume heartier foods very early in life, right? So we're going to think about how the alligator develops its teeth from the embryonic stage and into adulthood. The other nice thing about studying alligator teeth patterns is the fact that their jaw is more or less a parabola. So let me skip one slide further for now. This is a very good model of alligator's jaw. And again, as I just said, right, like it's a pretty nice looking parabola. The numbers on the right here correspond to the sequence in which alligator gets its teeth. So the general sequence is it will get teeth 1, 2, and 3 more or less simultaneously right away. And the next set of teeth is going to acquire are going to be teeth 4, 5, 6, and 7. And again, these come out more or less simultaneously. Then teeth 8 and 9, 10, 11, and 12 come again more or less together, and 13 comes around the same time but a little bit later. So what researchers were wondering is why this pattern and not some other pattern. So let's take a look at the positioning of these teeth. Notice that the jaw is obviously symmetric. So the teeth on the left correspond to the same as teeth on the right. So when I'm saying that teeth 1, 2, 3 come out, it's the tooth 1 and its friend on the other side. So the first set of teeth are teeth 1, 2, and 3. So these guys come out all together at the same time. The next set of teeth that come together are 4, 5, 6, and 7. Now, the first 3 teeth, maybe the pattern is kind of harder to notice, but this one makes it pretty obvious that the teeth are nicely, or at least visually, somewhat uniformly spread along the jaw, right? And this pattern is also easy, like 8 and 9, that's the next set. That's, 9 is right here. There's only 2, so it's kind of hard to tell anything. But 10, 11, 12 come out here. And again, they're not next to each other, but rather well spread along the jaw. The idea that has been suggested is that alligators acquire their teeth uniformly around the jaw so that they're always able to process food as efficiently as possible, right? If they only had the front teeth for a very long time, they won't be able to chew very much. If they only had the back teeth, same kind of problem, they wouldn't be able to tear very well. But this kind of very nicely spread out tooth appearance helps in the development. And this is what we can actually do. We can figure out, well, visually it looks like the teeth are well spread out. Are they really? So we can model this parabola with a very simple equation, actually. This is one that's presently on the picture. And as I said, the first 3 teeth appear more or less simultaneously. These are their positions in terms of x and in terms of y. And so what we can do is check to see, are these teeth really as evenly spaced out as we think they are. So what I would like to do is compute the distance between tooth 1 and tooth 2. Let's call it distance 1. And the distance between tooth 2 and tooth 3. Let's call it distance 2. The claim here is that they are going to be very similar distances, okay? And this is something that we can do with the help of the integrals. So to set up distances between the two teeth, knowing that this is what our function is, again, remember the arc length formula involves the derivative of it. Let's first of all take a derivative of it. So my y prime here is going to be minus 2 times 0.256x, and then the constant, of course, goes away. So this number here is minus 0.512x. Excellent. So for distance 1 here, I'm going to have an integral. Again, remember, it's all in terms of x. So I'm going to take my x coordinates as my limits of integration. So from 1.95 to 3.45, these are my x positions for the first two teeth. Square root of 1 plus, then my derivative, minus 0.512x all squared. And of course, dx. Okay, so this is the computation for the first distance. The computation for the second distance is going to be very similar. In fact, you won't actually, once you've set up your integral, all you have to do is alter limits of integration, because these are the only things that will change. Other than that, your function inside doesn't quite change because you're operating on the exact same curve as you were before, right? So my integral itself is the same, but now the limits of integration change. For D2, I would like to know the distance between the second and third teeth, so I'm going to plug in the corresponding points for the second and third x positions. Now, once you've set up these integrals, the issue is the same as before, in that if you take a look at what's inside, there's nothing to simplify. It's a square root 1 plus something squared. So this suggests trigonometric substitution. And instead of computing this here by hand, we can look up what it is using Wolfram Alpha or another computer algebra system. And so what I get for the first one here is that it's approximately 2.5. And what I get for the second one here, it's that approximately 2.4. So in fact, these distances are very close to each other. It's going to be even more close for the more teeth you gain, right? So again, like for example, teeth 4, 5, 6, and 7 are visually well spaced out. And if you set up integrals for them, you will notice that they are indeed very uniformly spread out across the alligator's jaw. This is our last application of the course. And I would like to leave you with the moral that I hope has been sort of the thread throughout the entire semester, is that nature indeed knows calculus. So the last animal we're considering is alligator, and alligator's teeth indeed follow some mathematical rules to be able to make alligator as efficiently as possible.